attendance.
All right. I'm gonna let me try to share
now
my
we are
screen.
live. Yeah, we are live. So welcome to everybody to the session on unique applications and methods. Our first speaker is Bati Camilete. So I think we can start with the session. Go ahead, Bati.
All right. Thanks, Emilio. And we are live. I am very, very pleased to be able to attend USAR 2022. By the way, I'm Bati. The R community is one that I am super, super appreciative of. It's done wonders for science. It has raised me literally as a developer. So in my own small way, this was a way to pay back to that fantastic community. All right. What am I going to talk to you about? I am going to talk to you about a statistical test, and I am going to suggest that this statistical test is probably one you want to be reaching for whenever you are in a situation where you want to test for, say, model performance or some sort of data monitoring situation. And that's the principle. So call me when it hurts, right? Imagine you happen to be the person who has the pager. You don't want to be woken up at 3 a.m. in the morning if the roof is not on fire. Okay. Before I maybe jump into the weeds and the details, the obligatory disclaimer. I work in industry for RBC. It's one of the largest financial banks up north in Canada. This talk, the views expressed in this talk are, of course, solely my own. Having said that, RBC was supportive and supported this work. I am infinitely grateful and also inordinately lucky maybe to work for a place where leadership believes in the value of research and goes out of its way to support it, including open source. All right. What's the problem? I happen to work for a model validation group. So what we do is we try to make sure that the models that are developed within the bank are working as expected. So one of the biggest problems that keeps us up at night when it comes to machine learning model is that of dataset shift. And what that is, put very simply, is imagine you happen to have trained your predictive algorithm on some training set, and now you have to predict on some test set that you have not seen before. The fear is that the training and the test set might not be at all alike. They could be very, very different. And as a result, performance will suffer on the test set because all of the examples that you're not predicting on don't have maybe a counterpart in the training set that the model has learned from. What's the common prescription? The common prescription in practice and in the literature, they will tell you, is to apply a test of equal distribution to make sure that those two samples essentially align. And I'm going to try to convince you that that is actually not such a great idea. As a maybe spoiler alert, there is the quote that I'm giving you there, which comes from a research group way back in Google, and they're already telling you that most practitioners tend to be distrustful of test of equal distribution. And there is a reason for that. Those tests of equal distribution are essentially too sensitive. They always tell you that the distributions are different, even when you probably shouldn't worry about the distribution change. And that, in essence, is actually the biggest problem with test of equal distribution with respect to dataset shift, is that they are prone to these false alarms. What they will do is that they're going to rightly detect changes in distribution. But unfortunately, most changes in the distribution are perfectly benign. They should be ignored, right? It's just a little bump in your density and your statistical test throws its hands up saying it's different. You should really not call for help. And so that's maybe the situation that we were facing, and we needed a statistical test that would do a better job of confronting these confronting data set shift. So what's a better question to ask as opposed to, are these two samples the same? A better question to ask is, are we worse off? Because this is what we want to know from a model performance standpoint. And that's actually the statistical test that I'm going to try to present to you here. Now, the method that that I'm going to present to you has a package that supports it. It's already on CRAN, should you be interested. So you could go and maybe use that on your own data sets as well. And I should add, the paper in support of this research has also been accepted at the International Conference for Uncertainty in Artificial Intelligence. That's UAI 2022. The presentation, I think, is in September. So if you're also interested in the gory details, I'll give you a reference at the very end to gorge on all the statistical details. Okay, so what's the wish list? Since we're going to be discarding these test of equal distribution, what we want is essentially, we do want a test. We want a test that's robust to false alarms, that focuses on unusual inputs, outliers essentially, that is flexible. And the flexible part is key because we want to be able to test for different notions of allowingness, right? So how is it that we define what a bad outcome is? In prediction settings, it could be somewhat easy. We all used to maybe dealing with residuals or prediction errors, but there are other notions that are complementary and just as good or as informative in their own right. Right? You could use things like prediction uncertainty and what have you. So one way to think about the framework that I'm going to talk to you about, DSOS, this statistical test, is that what it does is it takes arbitrary outlier scores and it turns them into interpretable probabilities, into p-values, which as statisticians, as data scientists, we all know and love. We've been doing this since the early days. So we're comfortable with that paradigm. And again, the framework is absolutely focused on testing for adverse shifts, not for equality, right? We're in a different world here. We're not testing for whether the two samples are the same. We're testing for adverse shifts. The question being, are we worse off? Okay, the proof is in the pudding. And it's usually best maybe to show you what it looks like in practice. So let me actually try to do that. Don't worry over much. I'm going to try to break down this plot in different components, but I want to draw your attention to a few things. On the x-axis, you already see 4 different dimensions. And these 4 dimensions are essentially different notion of outlieringness. How is it that we're going to judge our test set? As I mentioned before, we could do it through prediction errors. That's going to be the residual diagnostic part. We could do it using prediction uncertainty. That's what I'm calling confidence-based OOD. That's out of distribution detection, but that's not all that important. And so forth and so on and so on and so forth. Okay. So let me talk to you about the first case that you're actually seeing in this plot. That is the line in green that says random. What is it? Well, it takes a data set that we all know and love. We've used it to death. That's the Iris data set. And simply what it does is it splits it randomly. And it takes one part as the training set and the other part as the test set. And it applies these different tests of adverse shifts based on different outlier score. Now, the first thing I want to draw your attention to is what would happen if you were actually going to be testing for equal distribution. That's equivalent to the last row on this table, that the one that says 2 sample classification, where the outlier score is quote unquote sample membership. You could refer to the white paper if you need the details. But what's clear from that test is that test of equal distribution will essentially reject. It will tell you, you know what? The 2 distribution definitely look different. However, if you examine, if you evaluate this distribution on the basis of different notions of outlyingness. I would argue notions of outlyingness that you care about, namely prediction error, prediction uncertainty, and even sort of density-based wise. For all of those tests, DSOS tells you that we are actually not worse off. So this is a perfect example of a false alarm, right? According to two-sample classification, to test the equal distribution, it tells you the distributions are different. You should probably intervene. But when you squint a little more and you examine these other aspects of the samples, you realize that no, actually, it's as it so happens, you're perfectly fine. Right? So this is what DSOS does for you, because it kind of, one, allows you to go away from this sort of setting where you're only concerned about the distribution. You can interrogate your data with more, I would say, informative notion of outlyingness. So that was the first case. Let me tell you about the second case. And going back to this plot, that is the plot in reddish color, orange. I'm a little colorblind. I think that's orange. Correct me if I'm mistaken. And I hear an echo. All right. Oh, still hear an echo. But all right, I'm going to try to forge ahead with the echo. Okay, so the second example that I want to talk to you about, what happens? For this one, what we do is we make sure that the test set contains the highest density points from the iris data set. So essentially, the test set is cleaner than the training set. And if you are in that circumstance, what happens if you apply DSOS to it? Again, you realize that your test of equal distribution, your two-sample classification, are going to reject. They're going to tell you that the distributions are different. There should be a theme here. They almost always tell you that your samples are different, which is what you don't want. All right, so what happens when you examine the two samples based on other criteria? You'll see here that, again, prediction uncertainty and prediction error, if that's the notion of outlyingness that you happen to be using, will tell you that we are worse off. That's a bit surprising because if you recall, I was telling you that the test set comes from the highest part of the distribution, right? From the cleanest part of the distribution, if you will. So why would that be the case? As it turns out, this is because, of course, the highest density points are not necessarily the safest. They can be the most difficult one to predict. And having investigated that offline, I can tell you in this case, it's because iris, one of the two species of flowers that you have to predict, overlaps. And as a result, they are high density, but very difficult to discriminate against one from the other. And that's the reason why prediction suffers, while the distribution, on the other hand, doesn't seem to have been affected all that much. Thank you, Emilio, for the heads up. This is actually great, and this is where I wanted to spend the time because it gives you a flavor of what DSOS can do for you. So DSOS is this paradigm to test for non-negligible adverse shifts. I didn't tell you a lot about the theory, and I'm going to do that now in one quick sentence. Underneath it all, what is actually driving this approach, the test statistic that we're using, is the weighted area under the AUC. And I explain maybe in the paper in details why this is a great way to approach the problem. It's robust, and it does a number of other things for your benefit. Throughout the presentation, I sort of peppered a few slides with a number of references. As I mentioned, the paper has been accepted at UAI 2022. Should you be interested, there is the reference that you can actually hunt down and read about all the gory details. The other references have to do with defining maybe data set shift and whatever it happens to be on the slide deck. And I am right at the 15 minutes mark, and I think that's perfect because I will stop there. Thank you very much for humoring me.
Thank you ever so much, Bachi, for sticking to the time so close. So thank you very much, and thank you for the presentation. It was a nice presentation. Let's go to the Q&A section. We have one question. If any of the attendees have many other questions, please write in the Q&A panel. The question from Pierre Lafay is, why can't we just increase the significance level alpha of a classical test if we are afraid to get false alarms?
That's a great question. Thanks for the question, Pierre. The problem is twofold. One is that essentially test of equal distribution are testing for the wrong thing to begin with, right? They're testing for whether the two samples are more or less the same. But from a performance monitoring standpoint, that's not necessarily what we care about. So there is a misalignment of objective there. What we actually would like to know is whether we are worse off, right, from a particular reference point. So that's one. Two, I would say that raising sort of your alpha will not help you all that much. You're still in the same paradigm, and you get into the problem of p hacking, right? Someone reports a result telling you it's 5% versus 10%. That's not really where you should be spending most of your time. Those tests of equal distributions are going to be still subject to the same kind of problem, and worse yet, some of them are not robust. So if you take your maybe your favorite test of equal distribution off the shelf, it might not be the case that it is robust. So for 1 or 2 points, 1 or 2 outliers can completely ruin the results that you happen to get. You do want a framework that is robust. DSOS gives you that also out of the box. Hopefully that answers the question and gives you a sense of why this framework is better than going back to or trying to just change test of equal distributions.
Great, thank you very much for the answer. There are no more questions, but I have one. If it's maybe, have you considered or have you compared your method with functional data analysis or comparing profiles, nonlinear profiles? There are some methods that we use, for example, for multivariate processes that can be modeled as functions, and this is also very high dimensional data, like in the settings you comment, and this can be when you can model useful. Do you know that approach, or have you compared?
I do. I've seen that literature. I am not overly familiar with, and so I'm hesitant to comment all that much. I'll give you maybe a sense of the kind of comparison that we've done for this approach, and you can find that in the paper. One of the things that we've done is we've compared DSOS with what I would characterize as modern tests of equal distributions. These are some of the newest methods, the newest kids on the block, and to see whether we lose anything by using this paradigm, which tests for adverse shifts, as opposed to using a paradigm that purposely tests for equality of distribution. And the punchline is that in terms of power, you hardly lose anything at all. Relative efficiency of the two methods, they tend to converge. That is, if you are choosing the same sort of outlier score for both notions. However, again, for test of equal distribution, you're only looking at one particular aspect, right? The density estimation. You're not considering prediction. You're not considering uncertainty. You're not considering other things that you may care about. So DSOS does that. It extends beyond that one single axis. There are a number of other methods that are also really neat in the literature that will allow you to characterize changes in performance. I'm thinking, for instance, of non-inferiority tests, which are very popular in healthcare. But maybe I digress and I won't get into that. But suffice it to say that there are other ways that are also that you can bring to bear on the problem.
Okay, thank you very much again, and very nice presentation and responses to the questions. I think we can continue, and our next speaker is Asutosh Dalal. I hope I am pronouncing correctly your name.
Yes, sir.
And you can share your screen. Thank you. And you have 15 minutes. And then 5 minutes for a Q&A and transition between speakers. So go ahead, please.
Okay, sir. Thank you, sir. My screen is visible, sir?
Yeah.
Hello?
Perfect.
Hello everyone, welcome to my presentation. I am Asutosh Dalal, a PhD scholar from Indian Agricultural Statistics Research Institute under Indian Council of Agricultural Research, New Delhi, India. Today in this unique application and method session, I will be discussing about my two R packages, that is NBB designs and RSDNE for generating designs and data incorporating neighbor effects. Before going further, we need to know some basic terms for experimental designs. The experimental design is a systematic method to determine the relationship between factors affecting a process and the output of the process, deciding how the observations or measurements should be taken to answer a particular question in a valid, efficient, and economical way. Now, what is the purpose of experimental design? The purpose of experimental design is to determine the principal causes of variation in a measured response and to find the conditions that give rise to a maximum or minimum response, and also to compare the responses achieved at different settings of controllable variables. There are two types of experimental design based upon experimental material. One is block design, other is response surface design. Then what is a block design? This is a set of experimental units having the partition or blocks which represents the occurrences of the factors under certain parametric conditions. For example, randomized complete block designs, balanced incomplete block designs, partially balanced incomplete block design, etc. And what is response surface design? It is a sequence of experiments of the various settings or combination of input factors to provide an optimum solution of an experimental problem. Here, factors are assumed to be quantitative. Now, here we will discuss about one important concept, which is neighbor effect. Then what is neighbor effect? The response depends not only on the treatment combination applied to that particular unit, but also on the treatment combination applied to the neighboring units. For better understanding, uh, let us consider this is an agricultural field trial where a field is divided into plots. Now, if one plot receives a spray of chemical treatment, wind drift may cause the effect of spray spill over adjacent plots. If treatments are varieties, then neighbor effects may arise due to the differences in heights, root vigor, germination date for the small plots. And due to the neighbor effect, the estimates of treatment differences may deviate. Now, when we add neighbor effect in block model, then let's see what happens. And let us consider this is one block which having 5 plots. Now consider this middle plot, and when neighbor effect not added, then this model speaks all. where response is the sum of treatment effect, block effect, besides general mean effect. But when never effect is there, then this model will not work. So if we consider this left and right side never effect, then there will be a new model. Here this is a new model where new two extra terms are coming due to the left and right side never effect. Then in this case, this model will work very good. And now here this is an example for never balanced block design, which having the parameters number of treatments 5, number of blocks 4, and each treatment having the replication 4 and block size 5, and each treatment appears both left and right side as a never once. So if we exclude these two columns which are border plots, then this is like general randomized complete block design, because each treatment appears in each block once. But here we need to add this border plots, because to ensure never balanced property of this design. From the border plots, no observation has taken to measure the response variable. Now the question arises, how this never balancing happened. For that, we need to consider one treatment here. Let's say treatment number 2. Then we can see that in the first block, treatment number 1 and 3 is adjacent, and for the next block 5 and 4, and for the next 4 and 5, and for the next 3 and 1. So we can clearly see that each treatment appears both left and right side as never once. So this is never balanced design, and we can check it for any other treatment also. Now we'll talk about response surface model. Here, this is a general set of response surface model. Y is the dependent variable, and fxu is the function of all the independent variables, and eu is the error. Main motive of response surface model is to optimize the response. Mainly two models are used: first order response surface model and second order response surface model. For the first order response surface model, this is the function, and for the second order response surface model, this is the function. And when we add never effect here, then we can see the slight change in this model. And here the new term GUU dash equals to 1 if response coming from the same plot, and it is alpha when its response affected by the adjacent plots. Here alpha is nothing but the coefficient of never effect, which ranges from 0 to 1, and otherwise here GU dash is 0 otherwise. Here is the example of response surface design with never effects. Here two factor having two levels, +1, -1, and using border plots, this design is generated. This design is generated in such a way that this maintains constancy of variance of predicted response. Here, first order response surface model is fitted, and for alpha value 0.5, we can see that variance of parameter estimates is this, and variance of predicted response is this. This is coming constant. So this is also called the rotatability property of a design. And now we can see that there is impact never effect in response surface design also. Let's say there is 3 factors n, p, and k, each having 2 levels, +1 and -1. For this, there is a 2 cube experimental plots. Here for each there is response also given. This G matrix is never matrix, and here when never effect not added, then residual sum of square is very high, and R square value is very less. For this case, this is the model. And when residual sum of square is when never effect is added, then residual sum of square is very less, and R square value is very high. For this case, this is the model. Although this design is not rotatable, still the parameters become significant here. Many work had been done on never effects. Here some cited here. In block design setup, Ajes et al., Tomar et al., Jaggi et al. In response surface model setup, Sarike et al., Varghese et al., Verma et al. And this Jaggi et al., this is a book reference where design setup and response surface model setup is given. And there are few paid softwares available like SAS Design Expert to analyze this type of designs, but there is no software available for analysis of this design. So there is a need for that. As R is an open source software, so for easy accessibility of the designs, it is required to develop an R package for generation of this design as well as analysis. For this purpose, NPV designs and RSGNE two R packages have been developed. Here is the snapshot of NPV designs from CRAN repository, and NPV designs stand for Never Balanced Block Designs. And here is 6 function of that package, and here first one along with their parameters. Here analysis, first one is the analysis function. Input is needed a matrix of a given format, and then the NVPT1, NVPT2, and NVPT3. These will generate complete never balanced block design, and the rest two will generate partially never balanced block designs. User only give the V input, then this function will generate designs accordingly. So here this is the input. This is the input in R, and this is the output generated in R. When a user giving NVPT1 in the parameter range here 5, then this output will show the design along with their parameters and also information matrices. And here also example for partially never balanced block design, when parameter value is 8, then also this will give design parameters and also information matrices. A sample data also given within this package as a name sample underscore data as an illustration purpose. For analysis function, this type of data is needed. One can see these two ANOVA tables and can get the understanding of how never effect is important. For the first case, never effect not included, then using normal ANOVA function, we get this type of ANOVA table. And when we added never effect, left and right side never effect, then using our analysis function, we get this type of ANOVA table, and then we can see that left never and right never is highly significant. And here's the snapshot for package RSDNE, which stands for Response Surface Designs with Never Effects. It is having the 3 functions, sim function, sim1, sim2. But sim function is used for symmetrical case when n1 factors having s1 levels and s1 having the range 2 to 6 and n1 having the range 2 to 4. And sim1 is used for asymmetric factorial cases when n1 factors having 2 levels and n2 factors having 3 levels. And for here n1 n2 having the range 1 to 5. And sim2 function, it is also used for asymmetric factorial cases when n1 factors having s1 levels and n2 factors having s2 levels. And here s1 s2 having the range 2 to 8 and n1 n2 having the range 1 to 4. This is the output generated from R, and when from sim function, when parameter value given 2 to 0.5, which implies that 2 factors having 2 levels when alpha value is 0.5. It shows X matrix, Z prime Z matrix, inverse of Z prime Z matrix, and also total number of runs, variance of predicted response. This is also an example from that here function is sim1 function where input is given 2, 3, 0.3. So here it implies 2 factors having 2 levels, 3 factors having 3 levels, and alpha value 0.3. And as a conclusion, we can say that the concept of never effect has been discussed along the incorporation of the same in block design model and response surface model. Develop 2 R packages, NPV designs and RSGNE for the generation of designs, which ensures more precise estimation of model parameters and are suitable for experimental situation where never effect is suspected. Here, 2 R packages link is given which is uploaded on CRAN, and the NPV designs package also provides function for the analysis of data generated from such trials The design generated through these two packages and the analysis module would be useful for researchers working in this area. These are the references used while developing the our packages. And at last, I want to thank all the contributors, and thank you all the participants for your patience hearing. Thank you.
Thank you very much, Ashutosh, and thank you for the presentation and also for sticking to the time. There are no questions in the Q&A panel. Maybe the other speakers have another question. As we have the microphone open, we can take advantage of this, and you can make a question directly to Ashutosh.
Can you give us?
I have a question. Yeah, go ahead.
Oh, I was just going to ask if you could give ideas of applications for these packages. What type of research do you think it would help?
Application, it may be applied it can be applied in agricultural experiment and also industrial experiments where never effect is suspected.
Thank you for the question, Matthew. I had also a question because in the field there are quite famous or well-known designs like a split plot, where you also have into consideration the small plots within large plots, and at some point it's not as explicit like your method, but so far your method accounts for the left and right side. But do you plan to extend to, for example, having a neighbor on the top and a neighbor on the bottom?
I will try, sir, for that, sir. There is scope. I will try, sir.
Yeah, so I think you are sharing your whole screen, and we see this tunnel.
Oh. Stop sharing?
Yes, unless you want to share the presentation again. Okay, so was my question clear, or?
Sir, please repeat one more time, sir.
Oh, sorry. Yeah, I said that you have a neighbor in the right and a neighbor on the left. But do you consider extending the model to a neighbor on the top and a neighbor on the bottom?
In this package, there is only left and right side, sir. We are not still counting on that. After future, maybe there is any scope, then we will try for this also.
Okay, that's a good advance what you did, but maybe in some settings you can have these like matrix plots for the experiments.
Yes.
Okay, there are no questions in the Q&A panel, so I think we can thank Ashutosh again for his presentation and go ahead with the session. Okay, thank you, Ashutosh. Thank you.
Thank you.
Our next speaker is Alex Su. Hi, Alex.
Yep. Hello. Hi, Emilio. Hey, everyone.
Share your screen and go ahead.
Yep. It's 4 a.m. in Sydney right now. Pretty cold. Yeah. So there we go. Okay. Yep. Can you guys see my screen? Yep.
Yes,
okay.
Perfect.
Cool. So thanks everyone. Hi, my name is Alex, and today I'll be presenting what was my honors project on building an R package on Raspberry Pi. And this is for collecting and analyzing data that comes from sensors in a streaming manner. So we're talking about sensors like temperature sensors and light sensors and all kinds of different real life kind of natural data metrics. And I was supervised with Pierre, my associate professor Pierre Lafayette, assistant professor Pavlo Moczarowski, and assistant professor Fabien Navarro. So yeah, this package is on my GitHub. It's called Raspberry Pi R. So what is a Raspberry Pi? Basically, I want to talk about what, I'll kind of structure this presentation around what a Raspberry Pi does and what kind of applications it can have on research, as well as different areas of application. And we can bring it onto why this matters for people who are using R. So a Raspberry Pi, to put it simply, is a credit card sized computer that costs around 50 to 150 AUD, and it's widely popular. And it was designed as an educational tool just for learning programming and learning about electric circuits. But then it has expanded on many different like types of sensors that it can connect to and be actually used in a lot of research applications and small scale projects that you can set up easily at home, like the one that I have at home as well. And yeah, you can connect it to you can plug it in and essentially connect via Wi-Fi, and you can use your local computer to use something called a secured shell to connect into the Raspberry Pi and play around with the applications and desktop programs and stuff like that. So some of the examples of motivations that we kind of thought about of how Raspberry Pis are used in modern day applications includes in ecology, where people have built a sensor for monitoring plant growth, or underwater ocean sounds, and as well as imaging. And also there was an application for recording birds in the canopy and listening to what time they have made various different sounds, etc. And there's also industrial applications where you can put it on top of a drone and survey a orchid and look at the different types of the direction at which the like plants have grew over time. And so yeah, lots of exciting applications for Raspberry Pi, and there has been a large number of purchases in the recent years as well. So there has been a lot of growth in that area, and the areas that it spans from includes engineering and computer science, but recently there's also more growth in the natural sciences. So that's the part that we kind of want to focus on here. So the project that we want to work on was we've basically noticed that there is a Raspberry Pi application for many different languages, like in Python, in C, but there isn't really one that works for R specifically when we want to connect the large variety of R packages with the data that is coming from a Raspberry Pi. So, and that's why we want to bridge this gap and build a Raspberry Pi R package that kind of abstract all of these lower level sensor code into simpler functions. So yeah, the scope of this package is we're choosing R because it's very popular among statisticians and data scientists. It's also, we're also using a local, running it locally rather than passing it through the cloud, because we want to leverage this Raspberry Pi's computing power. It's a mini computer with, I think, up to 4 gigs of RAM. So there's a lot of wasted computing power if we just pass it to the cloud and let it run in the cloud, because that's already been done as well. We also want to support for special data type of data streams where data is continuously coming into the system indefinitely and kind of like overfilling the previous blocks. And the main reason for why we want to do data streams, well, as well as the traditional batch data set. So like you can collect data at a specific time and store it, or you also can pass it as a continuous form of data. And the reason why we want to support data streams is because with data stream, you can you basically can continuously apply your like your real-time applications, like for example, a mean calculation or variance calculation, as well as like different types of streaming statistics that you can process on the Raspberry Pi, but simultaneously kind of doing a separate reading process at the same time. So let me illustrate by an example. So if you have a ecologist who wants to record the time of a particular type of bird making noises throughout the day, they might want to do some pre-processing when they're passing in data into the Raspberry Pi. And this is when we can kind of use a data stream to process the data as they are entering, and only pick out the time at which there is a detect the time at which there's a particular type of bird that actually makes that noise, and then store that data. So you can kind of build a pipeline around that, around this data stream, rather than having to kind of build this on like a batch set of data and then process it afterwards. So by doing everything in kind of at the data collection part, you can kind of do a lot more with the Raspberry Pi and using its computing power as well. So I hope that makes sense. And so, yeah, some type of algorithms that we have applied was it's type of simple kind of univariate statistical measure, statistical like units like mean, variance. Also, there's control charts. There's something called Tukey region, which is a bivariate or multivariate way of visualizing data distribution. And there's also a type of Bayesian change point detection. And the potential type of applications that we can have for these type of charts include like monitoring for environments in a greenhouse, detecting anomalies, or visualizing the distribution of two related data metrics, like monitoring fish movement and sound, if we can plot that as a 2D space. And also we can detect different types of change points in a light source, etc. So here is an example of the control charts. Like we have basically an exponential weighted mean control chart, moving average control chart, and there is two upper and lower, like 3 standard deviations on this on this chart. So what this experiment basically did was that I applied a bit of like gas around that the sensor that I have connected onto my Raspberry Pi, And we can see there's a significant like deviation at around the 10 to 20 minute mark, 10 to 20 seconds mark. And this was collected continuously for around like 60 seconds and so on. And there's also, this is an example with Tuki region, and we have used the temperature and humidity sensor in our Raspberry Pi to collect a kind of a continuous, like around like 200 data points or 100 data points of temperature and humidity, and we want to check what's the variation in that over indoor and outdoor. So we can see that the variation is indeed bigger. And finally, for Bayesian change point detection, this was applying a light source, and we want to detect the changes in the light value. So I've blocked off the light for around 15 seconds, and that was a significant deviation, which we can see on the change point detection graph as well. So those are some applications that only a very simple range of applications that we can apply, but obviously there is a large variety of complex applications in R that you can use, and this is just a mere showcase. Yeah, but focusing on the package itself and what we have done, basically the problem that we try to address with integrating R with kind of the packages that, integrating R with the sensors was basically there's just no existing published applications on how to integrate these something called the GPIO pins with R, and those pins are what is needed to control the sensors. And what we've first done was we simply built a set of wrapper functions to kind of connect with these pins, and that's very easy. That's just kind of using an existing set of C library to build that way. And the second part, which was to kind of build an end-to-end data stream pipeline, we had to use a set of C and C++ functions to store data onto a shared memory. And the reason why we want to do that is we want to do a kind of a simultaneous reading and writing process at the same time. So we use these C and C++ functions to write memory onto a set of blocks, and R will then use on a separate program to reach out for these memory and read them into the R program and do analysis on that. So these two processes are separate, so you don't interrupt the writing process as we read, and vice versa. So some of the libraries that we've used include Wiring Pi, which is a C library to control GPIO pins. We used a Linux library called mmap, and also RCPP for translating C++ code to R. Yep. And finally, these are some of the sensors that we have used, which is temperature and humidity sensor. This is the experiment this is the setup that I have at home. I've also connected to the camera. And here are some of the current and future sensors. So current sensors, we include temperature, light, natural gas, and camera module. And there's also a vast variety of sensors that we can connect, including GPS, ultrasonic, etc. So this is what it looks like in process. Basically, a block of memory is being written at all points, and that will get wrapped around into the buffer and continuously. And these are some of the core functions. So one is writing memory and one is reading memory. And I'll just show you a quick demonstration to showcase what this application does. So in the middle, we have a writing memory block, and on the right, we have a separate process for reading memory and also processing that into Shiny and then sending it back to my local computer. So this is the final, that's the final result. So, and finally, so the current limitations of Raspberry Pi is that it doesn't support RStudio. So to access the package, we'll need to access it through Linux terminal, and the implications of the Raspberry Pi is that hopefully by using this R package and along with Raspberry Pi, we can allow researchers to kind of use collect data in a very low cost and autonomous manner. So it makes sense to kind of build a pipeline around that, and encourages further statistical development on data streams as well. In terms of future research, we want to incorporate more sensors for the package. So we welcome collaborators. We want to add additional graphical demonstrations from Shiny as well. And finally, the CRAN submission and JSS submission is on the way. So thank you very much for your attention. And I'm sorry I ran a bit late in time.
Thank you. Thank you, Alex. No problem. We just have less time for questions, but I will try to translate to. Well, the first question or comment was from David Barra. Good to see you, David, here again in our conference. He said even up to 8 gigas of RAM. I don't. It's not a question. I think it was what you were talking about. You were talking about the streams and these things. Yeah. If David wants to elaborate the question, we wait for a more concrete question. Veronica Scott, this question: is there a reason C++ was chosen over Python to interface with the sensors?
Yeah, that's a great question. I think C++ was the C and C++ had a library called Wiring Pi, and it's basically, we chose it because it's faster and it can interact with the terminal a bit. We know that Python also interacts, but we mainly choose it for the speed advantage.
Okay, thank you. Said that really cool. Can the package be split in two? One for online stats and the other the interface with Raspberry Pi. I can think of use cases where we want to use the online algos outside of a Raspberry Pi.
Yeah, so I suppose then we haven't built it around anything outside of Raspberry Pi yet, but that's a potential area of development to kind of pass this streaming data into a separate computer and then run it up there as well. Yeah, thank you so much.
Cool. Thank you very much again, Alex. Thank you, and we will continue with the next speaker, just not to lose more time. Our next speaker is Matthew Pokernick, or Pokernick. I don't know how to pronounce your name, sorry.
No worries, you're not alone. My name is Matt Pokernick, and yeah, well, thank you, and thank you for having me. I'm a principal data scientist at Oracle Advertising, and I'm going to be talking a bit about basically estimating who's watching TV commercials with imperfect data. And a little bit to echo Vathi's expression of gratitude to the R community. This is my second R users talk. My first one was in 2004, and this was in person in Vienna. And I'm grateful that they're doing an online version of this year and last year, but look forward to also meeting people again in person. So quickly to outline my talk, I'll give a little context of the type of problems we deal with, the data, the statistical methods, our packages that have been useful in our work, and a little bit about Oracle Machine Learning for R. Okay, so context. This is what our group basically sells to advertisers. This is a dashboard. Well, we are the researchers that help them help come up with the numbers for this dashboard. But if you're an advertiser and you wanted to see who you were reaching with different types of commercials, TV, digital, connected TV, you would you can use this dashboard to see I'm reaching so many million people with so many million frequencies. We do this at the household level, the individual level. The user views this and thinks this is a very wonderful data that allows you to see all this. And obviously, as you might imagine, in truth, we don't. We use data that is available. It's incomplete, it's biased. We very seldom have complete insight to any home, and this is what gives us our jobs, gives us our challenges. We also allow the user, the client, to drill down and see at a demographic level who's seeing different types of commercials and how this compares to US Census level. Basically, all the numbers we share are factored up and adjusted to represent the population of the United States. And again, the user sees this and again thinks we have perfect data, but obviously we do not. How does this data all flow together? To power that dashboard, we have a large collection of different types of data sources. We have, I'll call it large TV data, and this would be from TV manufacturers such as Sony or Samsung. If you plug your TV into the internet and click agree, somewhere along the line, there's a module there that will report in an anonymized way, this device saw this commercial at this time, and that data gets aggregated and shared with advertisers and people in ad tech. There's a smaller set of data we work with. That's panel TV data. That would be people who opted in and are compensated to be viewed watching their TV. A word about the scale. Large TVs, we might have 20 million devices that we could see. Panel data might be several thousand. Connected TV is Hulu, Apple TV. That's distinguishable in that when you watch TV in that manner, you can be targeted. Ads could be directed to you based on your demographics and viewing panel. Whereas if you're just watching the Super Bowl, you see the same commercials everyone does. And digital, what you would see at the ESPN or New York Times site. This all gets glued together through something called an identity graph, and matches is made from the devices, and that's a whole art unto itself, relying a lot on IP addresses and information gathered in different ways. From a statistical point of view, the interesting thing comes in to get those numbers that we share on the dashboard. We need to do a number of things, and what I'll talk about is correcting for bias. All the data on the left is not random. It's data collected at opportunity. And we want to adjust for biases before information is shared in the UI. And of course, people still really like their Excel files. So we give them Excel files. All right. So for the television data, we have the data that we could see, our sample data, and it could either be our panel data, the 5,000 households, or the large data, the 20 million TV IDs. And again, that's biased in the way it's collected, the way it can be observed. And we want to adjust that so that our counts, our estimates of reach, our estimates of number of impressions, commercials seen, reflects US Census data. The way we do this with TV is an algorithm called, it has several names, but it's called raking, or it might be called iterative proportional fitting or rim weighting. I like raking because that actually kind of nicely describes what goes on. And in this toy example, the reason people choose this, and this is common in surveys, commonly used in survey statistics, is you might lack information, target information on like joint distribution. So for example, you can get distribution of household sizes from the US Census, how many people live with 1 or 2 adults, 5 or more, and you might get income information in a certain way, but you don't have in your target population the joint distribution of okay, how many people have this income and this household size, and you're lacking that information, and certainly as you increase dimensions, you will be lacking that information. So what rim weighting does, so with your sample data, you have this joint information, and basically what rim weighting does is going back and forth across dimensions of a dimension or an attribute. It will, like in this example, first create weights so that the counts are adjusted by household income. So these could be weighted to adjust to reach the target population, which then will increasingly skew the household size proportions, and suddenly then you go down in the other direction and reweight it in that dimension. And you go back and forth until the weights don't change. And so you're going to get a distinct weight for each kind of joint probability, household size, and income. The R package that I've found very useful is a package called Iterate, and it's created by Tony Rodriguez and Devon Witherfall, and it's available. It's not in CRAN yet. It's accessible on GitHub. And basically the workflow is we need to do some data wrangling to summarize our target values, summarize our sample data, choose attributes, define bins, be careful that the labels and everything are consistently defined across both your target and your sample data. Use the iterate function, which I'll show how it's used. And basically, this gives us weights for each record and makes comparisons across attributes. And this is quite useful. There are statistics we can use to evaluate and compare different sets of attributes and how bins are defined. And basically, a nice way to think of it is you have your raw number of records, which would be the number of rows you might have, and an effective size, which would be the sum of the weights squared over the sum of the squared weights, or weights squared. And if all the weights were the same, you would have an efficiency that is 1. There is no free lunch in this exercise. There is cost. The more you want to fit other attributes, you have higher costs and efficiencies. There's some options we have and some guidelines. We choose relevant attributes that relate to what we are trying to measure, and that is like things that might affect how much people are viewing TV. Bucket sizes need to be defined. This isn't, basically for all attributes, the data gets binned and there's some latitude there. Sometimes you have the ability to collapse marginal distributions into a joint distribution. We could do that with age and gender. And there's a upper limit for max weight, and this comes at a cost of increasing the bias, but it limits the possibility that certain households, certain TVs would have extreme weights, which would become excessively influential. To look at how things might flow in, or how things flow in R, first there's data wrangling to, again, evaluate the target and sample data. And this is just generic ggplots, but it would show, this would be our target. This is the census distribution for age and gender for adults over the age of 18. I need to bin that, and again, this is just generic dplyr operations going on. I've defined bins. I should point out that certainly in Oracle and in many companies, we are only looking at data for individuals over the age of 17. So we filter that, we create our buckets, we come up with a list that gives me the proportion for each age. And that is an input I will need. Could do something similar for income. Again, I'm putting things into different buckets. And a lot of this is going to be driven by the availability of information you have at your target. So it's not as open a question as you might think. Getting to the heart of the function, the iterate function takes essentially a list as input, and the key points of the list are going to be the data you're looking to weight, and in this case, this data frame sample data is the data I'm looking to weight, and then the attributes you're looking to weight across. So in this example, I'm looking to create weights based on household size, gender, and age, and all of these are binned. And very nicely, elegantly, the function, again, takes this list. It asks if you want to permute, because depending on which dimension you rake across first, that can affect the results. And if you want a maximum weight, you can set this. And so we've chosen a max weight of 10, and we could see that this converges. This function generally converges, which is nice. And the cost of this weighting algorithm would be 77%. So for choosing these dimensions, there are very nice summary statistics or graphical interpretation of the results. And in this, the red would be our unweighted proportions. The blue is the weighted proportions, and the black would be the baseline. And if you get convergence, basically the weighted and the base or the target distributions are going to match exactly, but it gives you some insight into what part of your population is over or underrepresented. And I could compare this. This is a similar exercise, but I've kind of combined age and gender into joint distributions because we have the data in the target area to do this. And so in this fashion, we've used this method to weight our TV devices to account for the fact that we tend to see more people that are older, and there's an income skew as well. All right, those examples were randomized examples of the small data set. For large scale TV, we pick up a couple more attributes. DMA is a geographical feature that we can't use in the smaller data set because we'd run into a sparse bin issue. And anyway, that is the application. That is the way we estimate weights, again, for the TV, and this gets done nightly. I just wanted to say a word about Oracle Machine Learning for R, which was used here, but it's nicely subtly under the hood. This is my RStudio environment for this exercise, and you can see some of the objects would be an Oracle R data frame. And what this does in my work environment, our data is all stored on Exadatas, and Oracle Machine Learning for R basically allows me to use my R client Studio interface, but R is installed on the nodes of the database, which allows me to use dplyr type functions seamlessly. I mean, the code basically, you wouldn't necessarily know that it's not straight up dplyr, and allows me to wrangle data in a fashion that I'm very familiar with. And the toy example, obviously, that is easily fit into a data frame. The larger data, it's nice to leave it on the database and avoid moving it. And yeah, so the takeaways, the breaking algorithm, particularly as iterated through Iterate, has been very useful in us exploring different weighting scenarios, what we want to use for targeting attributes, and how we want to do bins, and how do we compare weights needed for different data sources. And it's very, I think, nicely elegant. Using this within RStudio and with OML for R gives me a nice familiarity. Basically as user and a statistician. I'm not a programmer. I get to leverage a lot of the nice utilities of dplyr without learning much new. And with that, I see I have 2 seconds left. Here's some references and the location of the package. And that is it. Are there any questions? Or
Okay.
I was curious if
thank you very much. No problem. It was just 1 minute ahead, but no problem. Well, we have one question in the Q&A panel by Matthew Camillote. Thanks again, Batsy, for your question. Hi, Matthew. By any chance, give confidence intervals for the final answers after weight imputation? Curious to know how uncertain these metrics intrinsically are. And thanks for the insightful talk, and deeply feel your pain about Excel.
Yeah, the quick answer to that is it doesn't provide confidence intervals. The closest we've done through basically nesting sets of attribute variables, you could see which ones are the most costly to include. Like our in-house estimates of household size or number of children in household is just way different than the census values. And so in order to include that, the efficiency drops way down, which makes us question whether we actually have the data we need on our end to model presence of children. That's the way we would use that.
Okay, thank you. There are no more questions, and I think this message says that session ends in. So I think we are done. Well, thank you again to the four speakers. A really nice session. A pleasure to chairing it, and thank you also to all the attendees. See you in the next conference. Thank you.
Hope to see you.
Thanks for sharing, Emilio.
Thank you.
Bye, guys.
Thank you.
Thanks, Emilio.
Thank you.
Thank you.
Bye-bye.